This presentation is delivered by the Stanford Center for Professional Development.
Let us refresh about where we were at the end of Wednesday. As we had talked about the vector form of the buffer, so the editor buffer that's backing the word processing client, and the two-stack version, right, where we're shuffling stuff off and on the before and after stacks to get things done. And when we were looking at the main 6 operations, we're looking at the 4 cursor movements and the 2 editing operations, right, that we had traded off where editing had been slow in the vector to where editing was now fast, but then these long-distance movements were slow because of the shuffling. And then there was a little discussion at the very end about how this probably increases our space requirements because we're now keeping 2 stacks that are each capable of holding the entire contents as opposed to just one vector here with its slop. So that was where we were at. We're still kind of in the pursuit of this holy grail of could we get it to where everything's fast? Is it always a matter of trade-offs, or can we just invest some more smarts and some more cleverness and hard work and squeeze it down to where we can get everything to perform efficiently? And so typically when computer scientists say they want something to perform efficiently, they're hoping for log n time or faster. Constant time is the best. Log n grows so slowly that in fact logarithmic time is effectively constant for all values of reasonable values of n up to millions and billions. And so typically anything that's linear or higher is often a weak spot that you're trying to look at, and certainly things that are quadratic or exponential are definite opportunities for improvement. So let's look at this idea of the linked list. So that both the vector and the stack we're relying on this idea that contiguous memory, right, is the weak link that was causing some problems. That in the vector, that's shuffling to move things up and down, or in the case of the stack version, moving things from one side to the other, right, was part of what we were working up against. And the linked list is what promises to give us this opportunity to have each individual character be managed separately, and that flexibility might help resolve some of our problems here. So what we're going to look at is the idea of implementing the buffer using a linked list. So if I have the characters A, B, C, D, E, I could have a linked list here where I'm pointing to the head cell, which is A, which points to B and C and D and down to the null. And so what I'm modeling it as in the private data section will be a little linked list node, right, with the character in there and a pointer to the next one. And then I'm going to keep 2 pointers, one to the frontmost cell, and then one that's going to model where the cursor is within the buffer. So rather than doing it as like an index was handy in the case of vector where we have direct access, right? Given the way the linked list works, right? Knowing that it's at the 5th cell or the 4th cell isn't really very helpful. It will be more helpful to have as a pointer kind of directly into the midst of things to give us direct access to where the cursor is. So let's think a little bit of that cursor, because there's an important decision to be made early about helping to facilitate the later work we have to do. I have the contents A, B, C, D, E. So we talked about how the cursor is actually between 2 characters. If the cursor right now is situated after the A and before the B, so what I'm modeling is A cursor B, C, D, then it seems like the obvious 2 choices for where the cursor might point is to A or to B. And I had said in the case of the vector, if it were index 0 or index 1, that there wasn't a really strong preference for one over the other. There is going to be a really good reason to pick one for the linked list over the other. Would you rather point to the A for where the cursor is, or would you rather point to the B? A. Exactly. So the idea is that when I'm the cursor position is there, the next edit actually goes in between the A and the B. So if I insert the character Z, it really does go right here. And if I'm going to wire that in and splice it into the list, that if I'm pointing to B, then I'm kind of hosed because I'm already one past where I need to build a slice in because I need to know what was behind it to bring it in. So in fact, pointing to the character behind the cursor gives you access to wiring this down to here and this into there and then updating the cursor to point to the Z without having to do any kind of the difficult backward traversal. So that strongly suggests what it is. It's going to point to A when it's between A and B, B when it's between B and C, and so on. There's another little point here, though, which is there are actually 5 letters, right, in the cursor, but there are 6 cursor positions. It could be at the very beginning, in between all these, or at the very end. And the way we've chosen it right now, I can identify all of the 5 positions that have at least one character to the left. Right? So pointing to the A means it's after A, pointing to the B is after B, and so on, all the way down to the E. But I don't have a cursor position for what representing when the cursor is at the very beginning of the buffer. So one strategy I could use, right, is to say, well, I'll just use a special cursor position of null. Right? I need one more pointer value to hold on to, and I could make a special case out of this, oh, cursor is null. Once I've done that, though, I've actually then committed myself to this thing that's going to require all my code to be managing a special case of, well, when the cursor is null, do something a little different than when the cursor is pointing to some cell. I'm going to show you a way that we can kind of avoid the need for making this special case out of it by wasting a little bit of memory and then reorganizing our list to allow for there to be a 6th cell, an extra cell that we call the dummy cell. So in this case, that cell would go at the very front. It would have no character. I just let the character field be unset. It's not really a character. What it is just a placeholder. And when I created the buffer to begin with, even when it's empty, it's always going to have that cell. I'm going to create that cell in advance and kind of have it sitting ready and waiting, and that cell never gets deleted or moved or changed. In fact, the head of the list will always point to the same cell from beginning of this object's lifetime to the end, so it will never change this at all. And the cells that follow it are the ones that are going to be changing and growing and rearranging in response to editing commands. What this is going to buy us is a couple things. First off, it's going to make it so that there is a 6th cursor position. So now when the cursor is at the very beginning, we can set the cursor to point to this dummy cell. Okay, that's one thing that we've solved by doing that. Another thing that we've solved is actually we have made all the other cells in the list, the ones that are being edited and manipulated, we've made them all totally symmetric. That previously, there was always going to be a little bit of a special case about, well, if you're the front of the list. We've seen that sometimes when we're doing inserts, on the stack and queue linked list, that inserting later in the list involves kind of wiring in 2 pointers, one to come in, one to go out. But there was a special case of, oh, if you're the very first cell of the list, then your out pointer is the same, but your incoming pointer is resetting the head. That case has actually gone away now. That now every cell in there always has a predecessor. It always has a previous, right? Something behind it. So actually there will always be pulling a pointer in and pulling a pointer out for every cell with character data that's being modified. And that means some of that need for that extra little handling of, oh, if you're the very first cell, has gone away. The very first cell is always kind of this dummy cell and doesn't require us to go out of our way to do anything special for it. So this is going to solve a bunch of problems for us, and it's kind of a neat technique. You'll see this used actually fairly commonly in situations just managing a linked list just to buy yourself some symmetry in the remaining cells. Okay. So let me look at some code with you, and I'm going to actually draw some pictures as I go. I'm not going to write this code in real time because I think it's actually more important to see it acting on things than it is to see me typing out the characters for it. But the mechanism, right, in the case of the buffer here, is it's going to have a head pointer, which points to the frontmost cell, and a cursor, which points to the character that precedes the cursor. So if right now the contents of the buffer is the contents A, B, C, and let's say that right now the cursor is pointing to A. Actually, I need my dummy cell. What am I doing? Let me move everybody down one. So maybe we just have my dummy cell and my A and my B. Okay. And so the cursor right now is at the very front of the buffer. So this is kind of what it looks like. It has 2 characters, the A and the B. And I'm going to trace through the process of inserting a new character into the buffer. Is that my local variable CP is going to point to a new cell allocated out in the heap. Let's say the character I'm going to insert is the Z, so I'll assign CH to this character slot in there. And then the next for this gets to what the cursor is kind of currently following the cursor. So the cursor is pointing to the cell before it, and the next field of that cell tells us what follows it. So if I trace my cursor's next field, it points to A. And so I'm going to go ahead and set up this new cell's next field to also point to A. So now I've got 2 different ways to get to the A cell, right? Tracing off the dummy cell or tracing off this new cell. And then I update the cursor's next field to point to CP. So I just copied, right, the idea that CP's next field was pointing to A. I copied it down here to kind of do the splice out. Now I'm going to do the splice in, which causes it to no longer point to A, but instead point to my new cell down here, CP. And then I update the cursor to point to this new cell. That just means that subsequent inserts, like the C is kind of behind the cursor after I've made this edit, that this cell now points down there. And so then this variable goes away when that method ends. And so now the new structure that I have here is head still points to the dummy cell. That never changes, right? Dummy cell now points to Z. Z points to A. Z points to B. And so whatever letter I'm using here. And then the cursor in this case is between the Z and the A by virtue of the fact that the cursor is pointing to the Z. A subsequent one would sort of do the same thing, right? If I typed out ZY after I did this, right, we'd make a new cell over here. It would get what was currently coming out of the cursor's field, the next field, right? We would update cursor's next field to point to this new one, and then we would update cursor to point to this guy. And so now following the list, right, dummy cell, Z, Y, A, B, cursor pointing to the Y, which is the character directly to the left of the cursor. And so inserting in any position now, front cell, middle cell, end cell, doesn't require any special case handling. So you don't see any if of things. And you notice that you'll never see an update to the head directly here. That the head was set up to point to the dummy cell in the constructor and never needs any adjusting. It's only the cells after it that require the rearrangement of the pointers coming in and out. When I'm ready to delete a cell, then the mechanism for delete in the buffer is to delete the thing that follows the cursor. So if I have ZYAB, this is the character that delete is supposed to delete, the one after the cursor. And so the first thing it looks at is to make sure that we're not already at the end. In the case of the linked list form of this, right, if the cursor was pointing to the lastmost cell, and then we looked at its next field and saw that it was null, that would be the clue. Oh, it's pointing to the very last cell. There's nothing that follows it. So we have a quick test to make sure there's something there to delete. There is something following the cursor. And in this case, since the cursor is pointing to the Y, we're good. It says, look at its next field. It points to A. It says, OK, call this thing old and point to that A. Now do a wire around it. So take the cursor's next field. And so this thing is where I'm targeting my overwrite. And copy out of the old its next. So no longer pointing to the A, but instead pointing to the B, and then deleting the old, which causes this piece of memory to be reclaimed. And now the contents of my buffer have been shifted over to where it goes Z, Y, straight to B. The cursor in this case doesn't move. It actually deleted to the right, and so whatever was to the left of the cursor just stays in place. So again, no need to update anything special for the first or the last or any of those cells, right? That the symmetry of all the cells past the dummy kind of buys us some convenience in handling it. Question?
What does the dummy cell look like?
So the dummy cell looks like just any other cell. It actually is a new cell T, and what you do is you just don't assign the CH field, the character field, because it has nothing in it. So it actually looks just like all the others. It's just another node in the chain. But this one, right, you put there purposefully just as a placeholder, so it doesn't contain any character data. So if you were ready, for example, to print the contents of the buffer, you have to remember the dummy cell's there and just skip over it. You tend to start your list like at heads next being the first interesting cell to look at, and then work your way down to the end. So it just is a little a node just like all the others, but you just know that the character data here is useless. It's not important. You didn't even write anything there. In the back.
Didn't delete used to go left?
It turns out the delete in this case goes forward. So you could imagine that in some other world it does, but the ones we have done so far have always deleted forward. So like the delete, for example, in the stack case, grabbed from the after stack. It's just it turns out it's done that way because it happens to simplify some other things. You can imagine that delete in reverse. What would it take? Well, you'd have to back the cursor up, and as we're going to find out pretty soon, that would make it challenging for the linked list. And so partly we picked a delete that made certain things work out a little better for us. So both of these operations, right, are O of 1. And this is where the linked list really shines, right, on this sort of stuff, is because If you have access to the point at which you want to make a modification, so if you're already kind of in the midst of the thing you're trying to rearrange, it's often to the linked list advantage because it actually can do these rewiring kind of in the local context. And even if there's thousands of characters that follow the cursor, right, it doesn't matter. And there can be thousands of characters preceding the cursor for that matter too. That the idea that there's a much larger context it's working in doesn't impact its performance. It's really just doing this local little rearrangement of the pointers. And that's a real strength of the linked list design, is that flexibility that doesn't rely on everything living in contiguous memory. So let's talk about the movement options for this guy. So right now I have the contents Z, Y, with the cursor between that and then the B following it, so 3 characters worth. Get rid of my other bits of things that are on the board. And then the initial 2 operations are pretty simple, and then the later 2 are going to be a little bit messier. So let's look at the easy ones first. Moving the cursor to the beginning. So that jump that pulls you back to the very beginning, very easy in a linked list form. If I want to move the cursor to the beginning, all I need to do is take that cursor pointer and reset it to the head, which is where the dummy cell is. And so by virtue of doing that, the character it points to is the one that's to the left, right, of that, and to the left of that, right, the dummy cell is one we're not counting, so in fact it's like nothingness that's there, and so that means that the first character that follows the cursor is Z, which is the initial character of the buffer. So that reset, easy to do. We have easy access to the front of the list, and so no special crazy code required. Moving the cursor forward, also an easy thing to do. Linked lists are designed to make it easy to kind of work your way from the front to the back, and so moving the cursor forward is advancing that cursor by 1 step. So in the array form of this, where it was like a cursor plus plus, in this, the comparable form of that in the linked list is cursor equals cursor next. It has a little if test there. All of the versions actually do have something comparable to this, which is like, well, if you're already at the end, then there's nothing to be done, so you don't advance the cursor off into space. We check to make sure that there is something for it to point to. So in this case, seeing if the cursor's next field is null, it's not, it points to Z, then we go ahead and update the cursor to there, which has the effect of changing things to where the Z is the character to the left of the cursor and then the YB follow it. So moving this way, getting back to the beginning and kind of walking our way down, easy to do. Now we start to see where the linked list causes us a little bit of grief. Moving the cursor to the end. So now, starting at the beginning or the middle or wherever I am, I want to advance my way to the end. I don't know where the end is, right? Linked lists in general don't keep track of that. That in the simple form of the singly linked list, I'm going to have to work to find it. So I'm going to have to take where I am and walk my way down. And this one actually just makes use of an existing public member function, the move cursor forward. It's like, well, while the cursor next does not equal null, which is to say while we are not pointing at the very last cell of the linked list, then keep going. So it'll advance cursor equals cursor error next. So it'll say, does the cursor's next field null? No. Well, then set the cursor to be the cursor's next field. Is the cursor's next field null? Take care of the 0. No, it's not. So advance the cursor to the next field. Is the cursor's next field null? Yes. So that would be the last thing in the buffer. And so if we have hundreds or thousands or tens of characters, whichever it is, right, and depending on how close we already were, right, it will walk through everything from where the current editing position was to find the end of the buffer, one by one, working its way down. The even more painful operation is the simple one of just moving backwards. If I'm pointing right now to that B and I'd like to get back to that Y, the linked list is oblivious about kind of how you got there. It knows where to go from here, but that backing up is not supported in the simple form. In order to find out what preceded the B, our only option right now is to go back to the beginning and find it. So starting this pointer CP at the head and saying, do you point to, is your next field the cursor? And this one says, no. And it says, okay, well then advance. It's like, is your next field point to the cursor? No, it's not. Look at this one. Does your next field point to the same place as the cursor? Yes. Y's next field points to the same place the cursor does. That must mean that Y was the one that preceded the cursor in the linked list. And so after having gone back to the beginning and walked all the way down, especially if I'm near the end, right, that's a long traversal. And when I get there, I can say, oh yeah, that's the one. Back it up to there. Walking all the way down. Okay. some good linked list coding, good practice in there, but again, a funny set of trade-offs, right? Anybody have any questions about any part of the code? Here we go.
For the end, why can't you just, could you set the address in a pointer, and then, if the person wants to go to the end, they just access that?
That is a great idea. It's like, so what about improving this? So right now, if all we have is a pointer to the front, and each pointer has only a pointer to the next, it's like, well, maybe we need to add some more stuff, right? Track some more things. Like, what if we tracked the tail? Right? Would that help us, right? If we tracked the tail, right, we could move to the end quickly, right? Will that help us moving backwards? No, but it solves one of our problems. So like you're onto something. Let's look at what we've got, and then we'll start thinking about ways to fix it, because that's going to be one of the pieces we're going to think about. So if I move to linked list relative to what I have, it's like a shell game. The O of n's moved. It used to be that editing was slow, and we didn't like that. Then we made big movement fast, and now we have this funny thing where moving in certain ways is easy, and moving in other ways is bad. So moving down the document is good. Moving backwards in the document, not good. Moving back to the beginning is good, but moving to the end is bad. But then editing in all situations is good. Another sort of quirky set of things. It just feels like, it's like that game where the gophers pop their heads up and you pound on them and they just show up somewhere else, right? As soon as you get sort of one thing fixed, it seems like something else, had to give. This, I think, actually would be my ideal editor, though, because it turns out I have exactly this working style, which is like, I'll be down at the end of the document and I'll have to be generating new things, and I'm getting tired and I don't like writing, and what I keep wanting to do is I go back to the beginning and I read that again, because I worked on that the most and it's nice. And so I go back to the beginning, I'm like, oh yeah, look at this, look at how lovely this is. And then I never want to go back to the end where all the trouble is, right? So I just keep going back to the beginning and editing in the front, right? And then slowly get back to the end, and then I don't like it again, I go back to the beginning. But I never actually willingly go to the end to face my fears. So this is the editor I need. Also has a bit of a kicker in terms of space. So if the space for a character is 1 byte, which it typically is, right, and the space for a pointer is 4 bytes, then each of those linked list cells is costing us 5 bytes, right, which is sort of 5 times the amount of storage that the character itself would have taken alone. So in the vector, right, it was fairly tight, a little bit more going up in that, but we've actually kind of blown it up by another factor of 2 even beyond the stack, which is not quite a good direction to be going. So let's talk about what we can do to fix that. I'm not going to go through the process of coding this. I'm just going to give you kind of a thought exercise so you can kind of visualize it. But that what we have here, right, is an information problem, right? We only are keeping track of certain pathways through that linked list. What if we actually increased, right, our access to the list? We don't need to have the full access of a vector. Being able to know the nth character, by number is not actually as far as we need to go, but we do just need a little bit more coordination between a cell and its neighbors. And so the 2 things that would buy us out of a lot of the things we're seeing here is if we added a tail pointer. So if I just add a tail pointer that points to the last cell, then I can move to the end quickly. You say cursor equals tail the same way I did cursor equals head. So what was an O of n problem? Now O of 1. The backing up, not as easily solved by just having one thing that's going along. I also am going to need, on a per cell basis, this ability to move backwards. Well, it's just symmetry, right? If A knows where B is, and B knows where C, and C knows where D is, what's to stop it from also just tracking the information going in the other way? So that D knows that it came from C, and C knows it came from B, and so on. And so having this completely symmetric parallel set of links that just run the other direction then buys you the ability to move backwards with ease. The other thing this would give you is that the tail pointer is almost not quite enough to give you the exact access to the intent. It gives it to you, but you also have to be careful about what is it going to take to update it. And so inserting can easily update the tail pointer. It's the deleting that kind of would get you into trouble. If you were here and deleting, you'd have to kind of keep track of making sure if you were deleting the thing that was the tail pointer, so you have to be a little bit careful about making sure you don't lose track of your tail. But once I have both of these in place, right, I suddenly have something that can move forward easily, O of 1, move to the front easily, O of 1, move to the tail easily, O of 1, move backwards, O of 1. So I can make all of my operations O of 1. All of them. Still, the deleting is still going to have to delete the individual cells. There's one place where it suffers, but that's a much more rare occurrence. And I can get all 6. It moves fast in every dimension, right? Inserts and deletes, all good. And there are 2 places we paid for it. One is certainly in memory. So a 4-byte pointer one direction, a 4-byte pointer another direction, plus the 1 byte for the character means we now have a 9-byte per character storage usage. And the other way, which is a little bit hard to represent with some number in a quantitative way, but actually is also an important factor, which is your code got a lot more complicated. That if you looked at the code for the vector or the stack version, it was a few lines here, a few lines there. So if you looked at the code for the linked list singly we looked at, it's like you got to wire up these pointers. Now imagine you got to wire up twice as many pointers, right? Not only do you have the in and out going in one direction, you'll have the in and out going the other direction. And just the opportunity to make errors with pointers has now gone up by a factor of 2. The idea that you could get a vector version of this up and running in no time compared to several days, let's say, of getting the doubly linked one working might be a factor to keep in mind. If you're kind of investing for the long haul, sure, work hard, but know that it wasn't for free, right? So you've got this 1 byte 8 points pointer, 89% overhead. Okay, that's a lot of overhead, right, for small bits of data. More likely, and this is actually the way that most modern word processors really do this, right, is they don't just make one or the other. It's not just an array or a stack or a linked list. They actually look at ways to combine the features of both to get a hybrid, where you can take some of the advantages of one type of data, but also try to avoid its worst weaknesses. And so the most common way they're going to do this is some kind of chunking strategy, where you have a segment of the buffer that kind of is moved aside and worked on in one little array. It might be that those arrays are 10 or 20 or a sentence long, a paragraph long. It might be that actually they're dictated by when you change styles. So all of the code that's in one font kind of gets moved into one chunk, and as soon as you change styles, it breaks it into a new chunk that follows to kind of keep track of both the formatting information. Depends on some of the other features that are present in the processor here, but it's likely what it's doing. Rather than having all 1,000 or 10,000 or 10 million characters in one data structure, they're actually kind of separated to where you have a little bit of both. So the most likely thing is that there's some kind of array strategy on a chunk basis. There's a linking between those chunks. And what this allows you to do, right, is share that overhead cost. So in this case, if I had every sentence in a chunk by itself, and then I had next and previous pointers, which pointed to the next sentence and the previous sentence, that when I need to move the cursor forward or backwards, that within a chunk, it's just changing this index. Oh, it's at index 2, but now it's moving to 3 or 4 or 5. And then when it gets to the end of that chunk, at the end of that sentence, and you move forward, well, then it follows the next link forward. Similarly, moving backwards, right? So within a chunk, doing array-like manipulations, and then as it crosses the boundary, using a linked list steps to get further down. And so when it needs to move to the front or the back, right, those things are easily accessible using head and tail pointers. When I need to do an edit, it operates in this kind of array-like way when there's space within that chunk. So you start editing within a sentence, then it would kind of do some shifting on that array. But the array itself being pretty small means that although you are paying that cost of shuffling, you're doing it on a smaller chunk. It's not 1,000 characters that have to move, it's 20 or 40 that have to move within that sentence. And that when you need to insert a new sentence or a new chunk in the middle, right, you're doing linked list-like manipulations to build a new chunk and insert and splice. And so you have that flexibility where the remaining characters around it aren't all affected by it. So you have kind of local array editing and global linked list editing that gets you kind of the best of both worlds. But again, the factor, right, is cost showing up in code complexity. Right, that what you're looking at is kind of space-time trade-offs. Well, I can throw space at this. Sometimes people will say that in computer science. Well, I can throw space at this and get better time. So the double linked list is a good example of something that throws space at a problem to get better time. There's a lot of overhead. Moving to the chunk list is, okay, well, I want to get back some of that space. I'm not willing to invest 90% overhead to get this. Can I find a way to take a whole sentence worth of thing and add a few pointers here? That means that there's only 2 4-byte pointers per each sentence as opposed to each character, and that really way reduces the overhead. But then now, right, the problem is still back on your shoulders in terms of effort, which is now I have both an array and a linked list and doubly links and a lot of complicated stuff flying around to make it work. So, but it does work out, and it's kind of the process that actually that designers go through when they're building these kind of key structures, to say, well, what are the options, and do any of the basic things we know about work? What about building even fancier things that kind of take the best of both worlds and mix them together and have a little bit of the weaknesses of this, a little bit of that, but none of the really awful worst cases present in the end result. So in this case, you'd have a lot of things that were constant time where constant was defined by the chunk size. So O of 100, let's say, if that was the maximum chunk size, to do these things, as opposed to O of n for the whole document. So kind of a neat little thing to think through. There was a time, just so you can feel gratified about how I have worked you very hard, but actually in the past I've been even harsher, was we actually had them build the doubly linked chunk list editor buffer. And now we have you build the singly linked chunk list PQ, and it's actually still very complicated, as you'll find out, but not nearly quite as hairy as the full-on both directions, every way craziness. But you can kind of imagine in your mind. All right, any questions about editor buffer? We've got 2 more data structures to implement. 2 more things that we've been using and happy to have in our arsenal that we need to know how they work. Let's talk about map first. And in fact, the strategy I'm going to end up showing you for map is actually going to be the same one we use for set, and then we'll come back and think of even another clever way to do map too. So we've got 2 things to talk about, which are binary search trees and hashing. And I'm going to do binary search trees first, and then we'll get back to the hashing second time around. So map is probably the, next to vector, probably the most useful thing we've got going in your class library there. That all kinds of things that do lookup-based activities, looking up students by ID number or phone numbers by name, any of these kind of things where you need to have this key and associated satellite information, and you'd like to be able to do that retrieval and update quickly, the map is the one for you. So if you remember, it's key value pairs. It's all about key being the identifying mark that allows you to find the associated value, and then the value is actually just being stored and kind of retrieved without examining it or using it in any interesting way. And what we're really interested in here is how to make this guy work very efficiently, and so efficiently being hopefully log n or better. If we could get that on both the update operations that add and remove things from the map, as well as the lookup operation, then that would please probably all of our clients immensely if we can get both of those going well. So I'm going to build you a map. I've probably got enough time to do that. That attacks it from using simple tools to start with, just to kind of get a baseline for what we can do. Vector, our old friend vector. Can't get too much mileage out of vector, apparently, because you can always find a way to kind of make it do something useful for you. Gives us the convenience of managing that thing with low overhead, direct access. Seems good. We make a pair struct that has the key and the value together. We store it into a vector, and then we may or may not sort that vector. And if it's sorted, there's probably some good reasons to think about what order to sort it in and what information to be using to sort that. And then we'll get value and add. I'm just going to go through doing it rather than talk about it. That we'll just go over and make a vector happen. So let's get over here into Xcode. And so let's take a look at mymap.h. And so actually, all I'm going to put in there is add and get value. And the other ones, like contains, key, and remove, can be an exercise left to the reader. But these are the 2 operations that really matter to us, right? Getting something into there and getting something back out. And so, as I said, I'm going to start by building this thing on vector. So let me go ahead and indicate that I plan to use vector as part of what I'm doing. So I define a little structure that is the pair, let's say. Maybe I'll call that pair even, that's just a nice word for it. So the pair of the key and the value that go together. And then what I will store here is a vector of those pairs. So they'll give me a key and a value. I'll stick them together in that little struct, stick them into my vector, and hopefully be able to retrieve them later. So given that I'm depending on only vector, I don't have any other information, I don't technically need to actually go out of my way to disallow the memorized copying, because vector does a deep copy, but I'm going to leave it in there because I plan on going some places that's going to eventually need it. I might as well just be safe from the get-go. The vector will be set up and destroyed automatically as part of just management of my data members, so actually I don't have any explicit allocation and deallocation. So if I look at my constructor and destructor, they'll be totally empty. And then add and get value are where I'm going to actually get to do some work. So before I implement them, I'm just going to think for a second about how this is going to play out. Let's say I'm doing a vector that's storing strings and their length. Let's say it's just a map of string to int. And if I do, m.add car. I want to store a 3 with it. And so on the other side of the wall, right, what we're going to do is make a little struct that has the word car and the number 3 in it, right? And then we package it into our array. And so then we get a second call to put something in like dog, also with a 3, right? Then we'll make a second one of these and stick it in our array. And so on. So the idea is to have the vector kind of really manage where the storage is going, and then what we'll just do is package it up and stick it in there. The one thing, though, that I have to think a little bit about, because it sounds like add should be pretty easy. It almost seems like what I need to do is something as simple as this. And I'll start to write the code, and then you can tell me why this isn't what I want to do. I say pair TP, and I say p dot key equals key, p dot value equals val, and then I say entries dot add p. Almost, but not quite what I want. What have I forgotten to take care of? If it's not already in there, right? So that this has to do with just what's the interface for map. What does map say about if you try to add for a key a different value? So in the case of this one, it didn't quite make sense that I would add something, but let's say I accidentally put car in there with the length 2 the first time, and I went to go fix it, right? That my subsequent attempt to ask it to store car with the proper value 3 doesn't create a totally new entry. It has to find the existing entry that already has car and overwrite it. So the behavior of add could be an add when it was not previously existing. It also could be an overwrite of an existing value. So in this case, we do need to find if there is an entry that already has that key and just replace its value rather than add a second entry with the same key. So at any given point, right, in this whole vector, there should be one entry for each unique key. So I have to do a search. And let me write this code first, then I'm going to mention why I'm going to decompose it in a second. If I do entries.size, I++, and then I'm like, if entries of I.key equals key, right, then let's break. But let me pull out I so I can get access to it when I'm done. So after this loop exits, right, if I is less than entries.size, then I know that it found a match. In the case where it went through all of them and it never hit the break, right, then I will have gone all the way to where it is exactly equal to entries.size. If it didn't, right, then I just have a place to overwrite, and I can say entries of I.val equals val. And then otherwise, I go through this process of adding a new one. I had to go hunt that thing down and replace it. That code, when you look at it, you can say, gosh, I feel like that code's going to be familiar, right? Because that idea of searching to find a match to the key probably is going to come in really handy when I need to do get value. That it has the same exact problem of, oh, I've got to go find that match. And so in fact, that kind of motivates the idea of like, well, why don't I just take this little piece of code and separate it out and do a helper that they can both use. I may not have planned for this from the beginning, but once I see it happening, I might as well fix it. So I can say find index for key, that given a key will return to you the array, the vector index at which that key is, or a -1, let's say. So I don't need to keep that anymore. So if it ever found it, it returns I. Otherwise, it returns -1. That can be our not found. And then I can actually use that up here. And then I can say if found does not equal -1. Then we do that. And then that tells us that this little piece of code is going to come in handy right up here in terms of get value. If found does not equal -1, then we can return that. And what is the behavior of get value if it didn't find it? Does anybody remember? I ask it to get the value in this case for the string, lollipop, and it's not there. Does it return 0? What does it do? Contract for get value. Remember? Oh yeah. Is that it raises an error. There is not a sort of general case return value you can produce here that will really kind of sufficiently describe to someone who's made this call in error what happened, right? I can't return 0 because it happens to be that sometimes I'm putting ints, but sometimes I'm putting strings or structs or other kinds of things, that there is no general 0 or -1 to use. So the behavior of get value is if you ask it to retrieve a value for a key, it ought to be there. So the corresponding implementation would likely also just go through the process of having contains key, which would call find index for key and check. That could be used by the client if they need to know in advance that it's really there. So let's see how I'm doing. Let's go back to my code here. And typing, not my specialty, and just see that I can put something in and get it back out would be a good first test to see that things are going as they should. Oh, no, it didn't like that. Oh yeah, find index for key. Find index for key was not properly declared in my .h, so let me go move it there. I'll put it in the private section because I don't want this to be something that is exposed outside of the implementation. That the idea that there is an index and that there is a vector is really not something I'd want to make part of my public interface. That's really just an internal detail of how I'm managing stuff. Something about what I did. Oh yeah, how about I use the right name for that? One more case. Yes. Let me just take a look at them both before I let the compiler tell me what is and isn't right about them. So they're both doing find index for key, doing a linear search. If it came back as not -1, pulling out the matching value or overwriting it, and then in the case of adding or raising the error. So the previously stored value for that is 3. And if I go and I do one of those tests that's always good to know is what happens if I ask it for something that doesn't exist, making sure that the error handling that I put in there does what it was supposed to do, right? Any questions about the code that I wrote here? So vector is always a kind of a good starting place for these things because actually it tends to use very simple things and tends to lend itself to easy code. But because of vectors constraints being a contiguous back structure, right, there's likely to be some performance implication. And in particular, right, in the unsorted case here, both add and get value involve doing a linear search. In some cases, it will find it quickly at the very beginning or even halfway through. In other cases, it won't find it at all and have to search through the whole thing. So on average, if you figure it's equally likely to be in any position or not there at all, it's going to have to look through at least half of them or more. And so we can say, yeah, they're both linear. If we change it to be sorted, which is the first obvious improvement to make here, then get value gets a lot faster because we can take advantage of binary search. I sort it by key, so ignoring the values just are satellite data, but stored in order of key, then, you know, all the A words, B words, C words, D words, whatnot, and so then blocking it down the middle and seeing which half to look at, and then looking at the quarter of there and the eighth of there is going to very quickly narrow down on where it had to be if it's there or that it wasn't there at all. So we can implement that in logarithmic time, meaning that if you have 1,000 entries, it takes 10 comparisons to find it or agree it's not there. If you double that, it'll take one more comparison. You go to 2,000, you know, negligibly faster, right? Even numbers in the millions, right, are still just, you know, a handful of comparisons to work it out and say 2 to the 20th, for example, is roughly 1 million. So 20 comparisons in or out. And so didn't look at 1 million things 1 million times over. However, that didn't improve add. Why not? Why does keeping it in sorted order not have the same boost for add as it did for get value? Can I do the same logarithmic search? What do I run into?
You have to move all elements over.
Yeah, you can find the place fast, right? You can say, oh, if I'm inserting the word apple, it's like, oh, okay, I can very quickly narrow in on where it needed to be. If it was there, I can overwrite it quickly, but in the case where it really needed to do an add, it's got to move them down. And so the old add, right, did all its work in the search and then just tacked it on the end if it didn't find it or overwrote in the middle. But the new add also has to modify the array to put it in the right place. And putting it in the right place means shuffling to make space. And so even though it found it quickly, right, it was unable to update that quickly. So it still ends up being linear in that case. Now, this is actually not a terrible result. As it stands, it's probably much more likely that you're going to load up the data structure once and then do a lot of searches on it and then infrequent additions. That's a pretty common usage pattern for a map. Just to kind of like you build a dictionary, right? Like loading the dictionary once could be expensive, but then people do tons and tons of lookups of words later, but you don't change the definitions a lot later or add a lot of new words. So this might be actually quite tolerable in many situations, that the building of it was expensive, but gave you fast search access. But really what we want to do is say, can we get both of those? So kind of driving the same way we do with the editor buffer, it's like, well, what if I just want both those operations to be logarithmic or better? What can I do? So I'll leave you with kind of just a little bit of a taste of where we're heading, is to think a little bit about what the linked list does and doesn't buy us, right? That the linked list gave us flexibility at the editing, sort of the local editing site, but it doesn't give us fast searching. Well, maybe we can take this linked list and try to add fast searching to the idea of this pointer flexibility to get kind of the best of both worlds. So that's where we're going to start on Monday, building a tree. So if you have time today, I'd love to have you come to Termin, and otherwise have a good weekend and get your PQ working.